Okay, so we'll take a quick look at the calendar. We just finished quiz number 2. That was last class. I handed back quiz 2, except for the people who took it with Sandy. I'll get it back to you on Thursday. So quiz 2 was okay for some people, not so great for other people. You guys know where you stand, and if you don't know where you stand, then ask me, and I'll tell you exactly where you stand. But again, if you're disappointed with your quiz grade, if you do better on exam 2 than you did on quiz 2, then your exam 2 grade will completely replace your quiz 2 grade. Okay? So it's on the books right now, but it goes away if you improve when we get to exam 2. That said, exam 2 is harder than quiz 2, so it would mean more work in order to do better on the upcoming exam than on the quiz. So this week, what's the plan? We're going to do 2.5 and a little bit of 2.6 today. On Thursday, we're going to finish 2.6 and do 7, and then spring break, and then we come back a week later. All right, so that's the plan. Any questions on the calendar? All set. Yeah, homework is due in the, but it's not like an excessive amount of homework. On Thursday, 2.5, and then when we come back from break, 2 sections. You know, it's just a regular amount of homework. Okay. So let's come back here to page 151, and we'll start with the objective. Okay, so we'll go to Marcy for the objective. Thank you. Let's go to Megan B, number 1. Okay, 2 words. It says with your group, but we're just going to do this together very quickly. There are 2 different words that go in those blanks, and the hint is they both start with the letter V as in Victor. Anybody know either of these words? The solution to an equation is the something of the something that makes the equation true. Any math words we know that start with a V? Variable is good. Which one of these is the word variable? And then Jessica, what was your word? Value is the other word. Value and variable go in there in some order. Which one is first? The solution to an equation is the variable or value? Value of the variable that makes the equation true. All right, so we're going to do number 2 together. We've got 3 equations for us to solve. The equations here aren't really that much more complicated than ones we've already seen, except for the fact that there are lots of negative numbers floating around, and we've kept them out of the algebra up until recently. So in order to solve this first one, 13 minus 8x equals 28, we have to move some stuff away from the x. We need to move the 13, and we need to move that negative 8. And we got to do it in the right order. So not required, but I'm going to go through the short little process of making my do list and then an undo list. For example, if we substituted in the number 99, just making up a number for the x, right? If I had to substitute in 99 for the x, what would I do first in order to do this arithmetic, this calculation? I'd multiply. I'd do 8 times, right? 8 times the 99. And then what would I do? I'd subtract, right? So then I'd do 13 minus the thing. That's kind of complicated. What if we do something like this? If I call that a negative 8 times 99 and then add 13, do we buy that that's equivalent to what's up here? Instead of doing 8 times 99 and subtracting, I could think of it as a negative 8 times 99 and then add. So if I'm going to undo, what's the opposite of multiplying by negative 8? Is divide by negative 8. And then what's the opposite of adding 13? Subtracting 13. But then there's just one last twist. For our do list, we go down this way. For our undo list, we know we have to go the other direction, right? Undo things in a reverse order. So let's actually solve this equation. I'll copy it again here. And what's the first thing we're supposed to do according to our undo list? Subtract 13. So that 13 is hanging out on its own. It's available to us. And we're going to subtract 13 from both sides. And on the left-hand side, I have negative 8x equals 15. Okay, forget the undo list. Just look at that equation. How do I get rid of that negative 8? Divide. So it's clear we divide. Really, the only point of this do-undo is that you get stuff in the right order. But now you can see why I wanted to do this funny business of calling that subtraction of 8x a negative 8. That's why. So let's divide both sides by negative 8. Divide negative 8, and then we just finally get our answer, which is x equals 15 over negative 8. Meg? It is, but the top number was not negative. It was positive 15. Yeah. Okay, 15 over negative 8 is a full credit answer. Some people are in the habit of converting every single improper fraction, that's where the number on top is bigger, into a mixed number. You do not need to do that. Not only is it risky in that if you make a mistake, I'm going to take points off, whereas if you just left it here, you get full credit. But if you're actually going to do anything with a number, having it in improper fraction form is far better than having it in mixed number form. So this is just like, as a default, I'm not a fan of mixed numbers. Leave your answers in improper fraction form. Other thing about this, typically if there's one negative in a number, we know that the negative could be on top or on the bottom or in front. Remember we did that little puzzle with the blank boxes? And so again, this is a full credit answer, but I would not write it that way. If I saw a negative either place, I would say, oh, it's a negative 15/8. Just make the whole fraction negative. That step is not required. Just telling you what most math folks would do. Okay, let's take a look at the middle one here. Negative 2 equals 4 minus 5x divided by 7. We're going to do this without the do-undo list, but if you like the list, then make them. Can you guys see? I mean, there's a lot of numbers over here near the x. There's a 4, there's a 5, there's a 7, there's a subtraction. Lots of stuff has to move. Can you tell what the most available number is to move out of this list? 4, 5, 7? Which one is like freest? It's the 4, right? The 4 is just hanging out way far away from all the action. So the 4 is really the only thing that we can move right now. It's the only thing available to us. So let's go ahead and subtract 4 from both sides. So, okay. On the left-hand side now, negative 2 minus 4. Remember all this stuff about arithmetic of negative numbers that I've been saying for a month? You need to get to a place where you can do this. We are at that place. And if you are not able to solve these negative number problems, you're going to have no chance at doing the algebra, because embedded in the algebra is all this negative number arithmetic. That said, it's not the end of the game if you're not there today. But you got to get there really soon, and ask me after class, and I will give you resources to help you get there. But as of this moment, I'm assuming you can do negative 2 minus 4 without batting an eye. Negative 6. On the right-hand side, the 4's cancel. I'll copy that subtraction symbol. 5x over 7. Okay. Next thing to do, we need to move the negative, we need to move the 5, we need to move the 7. Here it actually doesn't matter which one you do first. I like to get rid of fractions. What's the opposite of this? Divide by 7. Multiply by 7, or multiply both sides by 7. So this guy times 7 and this guy times 7. Left-hand side, more negative number arithmetic. 7 times 6 is 42. We know that. But you also need to know how to deal with multiplying a positive number times a negative. What's the answer? Negative 42. Okay, right-hand side. Really, really common error to make. Don't copy this down because it's wrong. 7 times 5 up here gives me 35. 7 times 7 down there gives me 49. It's just not right. Yeah, the point of putting that 7 up there was explicitly to cancel it with the 7 in the bottom. Furthermore, that 7 is really 7 over what number? It's really 7 over 1, and we know we multiply across. So if you really insist on actually doing the multiplication, the 7 is really only where? Upstairs or downstairs? Only upstairs. So under no circumstances can that become a 49. But really, Tyler's got the right idea here. We put it there to cancel it. So there's no point in even doing any multiplication. We just cross it off and copy what's left. Negative 5x there. Okay, and then finally, this is a negative 5 times. What's the opposite of that? Divide by negative 5. So divide both sides by negative 5. Negative 5 here. On the right-hand side, we just get x. Left-hand side, okay, so essentially you're just going to copy that answer, negative 42 over negative 5, and that's it. Reduce it if you can, but nothing goes into 5 and 42. Don't change it to a mixed number. It's a waste of time. But there is one simplification that we have to do. It's really positive. Anytime you see a negative divided by a negative, you are obligated to cross them both off and make it positive. So 42/5 is our final answer. Okay. I mean, you showed that it's two negatives by showing the work involved. You don't need to write anything more. Just change it right away to positives. Okay, the last one in some sense is the simplest equation up here, but it's included for a specific reason, so let's give it a shot. I see a negative 16, and then there's an invisible negative 1 in front of that x. Which of those two numbers is available to us? It's that negative 16. It's far away from the x. So what's the opposite of that? Add 16, both sides. No, we're just adding 16. Yeah. So they cancel. And what's left on the left-hand side? Negative x. And then over there we do the addition 27. So this step right here is why this problem is included. Our final answer needs to look like x equals, right? Negative x equals is not allowed as a final answer. So the only question is, how do we convert this to the right answer? Add 1, divide by 1, divide by negative 1. That's the right thing to do, because there's an invisible negative 1 here, and so that means negative 1 times x, right? And so what's the opposite of multiplying by negative 1 is dividing by negative 1. So we divide both sides by negative 1. What happens on the left-hand side? We just get x. That's the goal. Okay, on the right-hand side, we got to clean up. You can't leave 27 over negative 1 as an answer. So first, is it going to be positive or negative when we're done? Negative, because there's a single negative sign. So I'll put a negative first. And now that I've handled the negative, it's really just 27 over 1, which is 27. So that's our answer there, negative 27. So again, that example is included to let us know we can't stop. If we get negative x equals, we have to go this one step further. Nicole had the right idea by dividing by negative 1. Okay, I'll put the flags out and I'll come around and help, but see how far you can get on the classwork. And in a while, we'll come back together and start the next section, but we've got some time. We start here at the top of 156 with a new objective. Can we go to Tyler here? Objective, are you on 156? Not quite. Right up there.
This lesson we saw
Inequalities.
Graph the solution on a number line and give examples of values that are or are not.
Good, thank you. So let's try number 1. We'll go back to Matt. Okay, so this is the first time we are thinking about an inequality other than things of the form x is less than or equal to 7, x is greater than 4. Remember we tackled these a few classes back? And we would graph them on a number line and shade in and decide whether to graph left or right. So we tackled those. What's the difference between those ones that we did and this new one that we didn't do? Yeah, it's not just X, right? When it was just X, those are the ones that we tackled last time. But now there's some stuff floating around beside the X. Now, some of you might already know how to solve the inequality. We're going to get there, but it's going to take us a few minutes before we do. So right now, we're going to kind of take our time and figure out what the solutions are to this X plus 2 is greater than 5. So we're just going to think, and we're going to name some values of X that make this inequality true. Can anybody name a particular number for X that you can plug in, and it makes this thing true? So I heard X equals 3. So if we plug 3 in, we get, what do we get? 3 plus 2 is 5, is greater than 5. Is that true or false? That's false. So actually, 3 doesn't work. I'm going to put in, remember how we had this open circle to say this is not included? So 3 doesn't work. We'll put an open circle there. How about X equals 4? 4 plus 2 is 6. Is that greater than 5? Yes, 4 works. Holly suggested 7. 7 plus 2, is it bigger than 5? Yes. And so I'm starting to feel like there's this whole long collection of numbers that are big enough to make that thing true. Let's see if we can find some more that make it false. Somebody give me a number that makes it false. 1. If we plug in X equals 1, 1 plus 2 is not greater than 5. So I'll put an open circle at 1 because that one didn't work. Heather suggested -2. How much is -2 plus 2? 0. Is that bigger than 5? No. So I'll put an open circle there. So we've got this whole long list of, I feel like, a bunch of open circles on the left, a bunch of filled in circles on the right, but we've got to find exactly the cutoff point. Now, I can see somewhere between 3 and 4 is where the magical cutoff has to be, because 4 worked and 3 didn't. How about 3.5? Yeah, X plus 2, 5.5. So 3.5 works. How about like 3.1? 3.1 would give us 5.1. So it feels like actually the first person yelled out X equals 3. I think that's actually a relevant number for this guy because that's the last number that doesn't work. Anything just a tiny bit bigger than 3 is going to be okay. So then for us to shade that in, the open circle would go at 3 just like we did, and then we'd shade in everything out this way, nice and thick, and then an arrow going to the right. It's open, which is our way of saying 3 doesn't work, but 3 is the last number that doesn't work. And there's actually no way to find the first number that works. Like we said, 3.1 works, but there are smaller numbers that work, like 3.01 and 3.001. And so there's no way to pinpoint the first number that works, so that's how we symbolize it. And putting open circles on these other numbers was overkill, and like we would never do that, but we were just kind of feeling our way in the dark here, and this is what we end up with. Okay, so we've shaded in all the numbers that make the inequality true. If I wanted to say this set of numbers that I've shaded in red in English, what would I say? All the numbers that are greater than 3. Greater than or equal to 3? No, 3 didn't work. So all the numbers greater than 3. So that's what we can write in English. All the numbers that are greater than 3. And then how do we write that in symbols? First symbol is a letter, X. And do you know which direction the greater than symbol goes? Yeah, it's going to eat the X. Greater than 3. So we started with this inequality, X plus 2 is greater than 5. And we ended up with the solution, that's what we call this thing here, X is greater than 3. And we're going to see very soon a shortcut that will just zip us there without playing this number line game. But let's play the number line game one more time with this guy. -2x is less than or equal to 6. So we're going to pick some numbers that work and pick some numbers that don't work, and we don't need to know which ones are which as we're picking them. Somebody name their favorite number? All right, I heard x equals 2. I heard x equals -3, but those are clearly people that know what's going on already. So let's pick some other numbers. We'll get to -3. So x equals 4 is good. How about let's pick some negative thing out here too. That one's already there. Yeah, let's pick another one. -2. Good. So we've got 3 random-ish numbers here, and we're going to try them all and just see which ones work and which ones don't. This one's going to be trickier because of that negative sign. So for example, this guy, it would say -2 times x, right? That's what the inequality says. So -2 times 2 is -4. And the question is that less than or equal to 6?
Yes.
It is. So x equals 2 works, which means how do I mark that on the graph?
The dot.
Filled in, right? X equals 2 worked. Everybody see where we plugged in? It's this thing that we're plugging into. So we're just changing the x to these numbers and deciding whether that statement is true or false. So now we'll plug in x equals 4. So when we plug 4 in for x, what do we get here? -2 times 4 is -8. Is that less than or equal to 6? Yes. So x equals 4 also works. So we'll fill that guy in. And then we pick this number -2. Now we got to be really careful because we got lots of negatives floating. So this says -2 times -2 is +4. Is that still less than or equal to 6? It is. So actually we haven't found a number that doesn't work yet. Can somebody pick some number like further out here to the left?
8.
So
-8.
All right. So let's try one more number because we haven't found one that doesn't work. X equals -8. So if we plug -8 for the x, -2 times -8 is +16. Is that less than or equal to 6? No. So finally we found a number that didn't work. And it was way out here at -8. Yeah, so we've got this collection, and -4 is maybe a good one to try. Like the cutoff is someplace in here, right? Because -2 works, but -8 doesn't, and someplace in between is the magical number. So finally, we're gonna come to the people that said -3 at the very beginning of this problem, and we're gonna figure out how they got that. But let's just plug that in and see what happens. If we plug -3 for x, -2 times -3, 6. Is 6 less than or equal to 6?
Yes.
Yes, but just barely, right? So it seems like that's our cutoff. That's our magic number because it just barely made this thing true. So we'll plug -3 and say this is the, I don't know, magic number. Don't share that outside of this class because nobody else will know what we're talking about. But that's the magic number, right? That's the cutoff. So anything left of that number is bad. Anything on or to the right of that number is good. So let's shade in all of those guys, starting at -3 and then going out here to the right forever.
So when it's like less than or equal to, shaded it at that number.
Yes, if it's an equal to, it gets filled in. Okay, in English, these are all the numbers that are what? Greater than or equal to, not 6. Just look at the number line. -3 was the magic number. It says magic number. So all the numbers greater than or equal to -3, that's what we can write in English. All the numbers that are greater than or equal to -3. Okay, and then in symbols, the first symbol is a letter, X, greater or equal. Write down the greater than or equal to sign. Are we all 100%? Which direction that one is?
Less than equal to.
I think this is greater than, right? Look at what we shaded. We shaded all the numbers that are bigger than 3. Yeah, we've written this correctly in English. It was all the numbers greater than or equal to -3. So is it this symbol or is it this symbol? Second one, right? Greater than with the line under it. Thank you, John. -3. The 6 is not part of the solution. The 6 didn't appear when we plotted these points. -3 was the magic number. Okay, and again, we started with an inequality. It said negative 2x is less than or equal to 6, and somehow that led us to the solution, x is greater than or equal to negative 3. All right? Okay, let's go to the next page. Number 3. We'll go to Geneva. Could you read 3, please? Yes.
Now, let's look at these two inequalities. In very shortcut that we can use to get
Okay, so let me just write down what the solutions were. We did all that work on the previous page. What was the solution to the first one we did? X. What was the solution? It was x greater than 3. That's what we got first, right? And then the one that we just did, x was less than, it's greater than or equal to negative 3. Those were our two solutions. So the question is, do we have to go through that whole long process with finding numbers that work and finding numbers that don't in order to solve? And the answer is no. Can anybody think of something we could do to both sides of this thing that will lead us to the answer, which is x greater than 3? Subtract 2, right? If it was an equal sign instead of a greater than, you would just say subtract 2. Okay, well, inequalities work almost exactly the same as equations. We'll subtract 2 from both sides, show our work here. And then what do we have on the left-hand side? X. And then we copy, it's usually an equals, but here it's a that. So whatever it is, you copy, right? And then 3. Super. There's our answer, and a whole lot less painful and time-consuming than that plotting points. Okay. Sneaky. Let's try this next one. Divide both sides by negative 2, right? That's what we do because it's a multiplication. So we're going to divide by negative 2, divide by negative 2. What happens on the left-hand side? X. We copy that symbol. And how much is 6 over negative 2? It's negative 3. Is that the right answer? That's not the right answer. It's not. Look at the answer is up on, it's in blue at the top. What I did was copy that thing in the middle. It was a less than or equal to. I just copied it. No funny business. But we divided by a negative number, which apparently means things are a little bit different than with equations. So this is not right. So here's our bold thing. We'll get Eric, can you read this first bullet? All right, that's so important. We're going to have Eric read it again. That's it. That's the only thing we need to know about inequalities compared to equations. That's the only difference. So everything that you know about solving equations is still valid here with this one little warning. If you multiply or divide by a negative, a bell and lights have to go off in your brain that says, wait, there's something different here. You got to change the direction of that inequality. So this guy at this moment changes over to that symbol, which is the right answer. Okay? So this is something that I'm assuming, I think most of you have seen before, this rule about if you divide or multiply by a negative, you got to change the direction. But let's spend 60 seconds talking about why that is true. So let's take a look at these two number lines. Well, yeah, let's take a look at these two lines. So we've got certain numbers highlighted on our first number line, and the negatives are out here on the left where they normally are. Yes, no funny business there. What we're going to do is divide each number by negative 2. So for example, if you take this number right here, negative 4, and divide it by negative 2, because that's what I'm going to do to all of them, what do I get? 2. So what I'd like you to do is just fill in, take each number and divide by negative 2. So carefully fill in those other 4 numbers. Okay, what do we get first? Negative 2 over negative 2 is 1. 0 divided by anything, 0. 2 over negative 2 is negative 1. And then over there, negative 2. Are these in the normal order for number lines? No, they're backwards, right? The negative should be out here on the left. The positive should be on the right, but they're in the wrong order. So apparently, when you divide by a negative number, you take that number line and you pull it off the board and flip it around and then put it back, right? Because when you multiply or divide by a negative, you're going to change the sign of every number. All of these numbers change signs when we came down here. And it would have been the same if instead of divide, it had said multiply, right? It would have been different numbers down here. For example, how much is -4 times -2 is 8, and that one's 4. But the important thing is, yeah, the positives are still going to end up out here. Everything gets pulled off and flipped around when you multiply or divide by a negative. So this is why we do it. Okay, so let's go to number 5. How does that look? Okay, so let's give it a shot. So the first thing we need to do is move one of these numbers. There's only one number that's available to us at the moment, and it's the 3. Everything in the parentheses is covered up right now, right? Nothing in the parentheses is accessible. So we got to first deal with that 3. This says 3 times. What do I do to get rid of that? Divide. Divide both sides by 3. Now a little warning bell is going off in my head, and maybe it is in yours too. Whenever I have an inequality and I'm multiplying or dividing, I got to think, I got to pause and say, oh, is this the moment where I change the direction of the inequality? When do you change the direction? When you multiply or divide by a negative number. So this is a +3. We don't do anything except pause to make sure we're not supposed to do anything. On the left-hand side, what happens? Cancels. And so we just get the stuff in the parentheses. And in fact, I don't even need the parentheses anymore because I've gotten rid of the multiplication that the parentheses indicated. That inequality stays the same direction. -15/3 is -5. Yeah, do you guys remember the implied parentheses when we had fractions? Where are they in this one? Up on the top, right? So you don't need to put them, but I'm going to put them to highlight that nothing in the parentheses is available. So the only number that's free to us is what number? Is that -2. It's the only one that we can touch right now. So this says divide by -2. What should we do to opposite that is multiply by -2. So I'll put it over here. Multiply this guy by -2. Multiply this guy by -2. What happens on the left-hand side? They cancel. Don't you dare multiply anything. You just put it there so it would cancel. So I'm just going to get 7 minus 4x, and I don't need those implied parentheses because we got rid of it. I'm going to do the right-hand side, and then we'll come back to the symbol. Multiply those two. What do we get? 10. And this is the moment we got to flip because we multiplied or divided by a negative number. So we just change the direction. The equal stays. All we're doing is changing the direction of the inequality piece. So if it was maybe equals in the beginning, it's going to be equals all the way through. Okay, which of these two numbers is free to us? 7, it's floating out here off on the side. What do we do to move it? Add 7. Subtract 7. Both sides. Okay, left-hand side. Don't say it out loud. I'm going to go to Matt. Matt, what happens on the left-hand side? Tell me what's left. Yes, what's left? That's what you said before, and I call on you because I want you to say the right thing. -4x, right? We move the 7, the subtraction symbol, the negative symbol is still there. 10 minus 7, that's easy. We subtracted 7. Do we need to change this? No, it's only for multiplication and division. So it stays exactly the same order.
So if it was multiplication and division, we would keep switching it back and forth.
Yes, every time. Every time you multiply or divide, you flip it. Doesn't matter how many times you've done that in the problem. Okay, last step. How do I move that -4? Divide by -4. So now we got to change it again. I know that inequality just needs to make up its mind. Okay, what do we have on the left-hand side? X. I'm going to forget the inequality for a second. The right-hand side is 3 over -4. It's a full credit answer if you leave it that way. But again, Mathematicians would always take that negative and move it to the front of the fraction. What happens to the inequality because we divided by negative? Flips again. There's our answer. Just go back and forth as many times as the problem dictates. Questions on that? Okay, while this is fresh in your head, you have 5 minutes and a change to try solving some inequalities. So let's see how far you can get here, and then we'll pick up here next time.